see what we can do. You fly in a balloon and you're above the atmosphere and it's great, but you only get a couple hours of data. Why don't we take it to a place where we can get years of data? Now, it wouldn't be as good in terms of per hour, but integrated over many years, it can be a real killer. So we took the actual balloon experiment. I put it on literally a Nike Ajax radar trailer from the Cold War, right? I took it, I rebuilt the whole thing, put a motor on it, put a pointing system on it. We put it on a boat and we rolled it up the mountain and we stuck it there for, 2 seasons at 6 months each. And we discovered the first peak in the cosmic microwave background power spectrum. That's kind of fun. So what do we do next? And the answer is you do something like ACT.
I was a graduate student at Harvard, and I met at a party this guy named Lyman Page, who was a graduate student at MIT. And he told me about the work he was doing, making, aiming to make some of the first, what would have been, in some ways, the first detection of the fluctuations. They were not confirmed until the Kobe results, but the first measurements in some way were in Lyman's thesis. A few years later, Lyman Page and I found ourselves both as young faculty at Princeton. And we began working together back in 1994 on a project that would grow to become WMAP, the Microwave Anisotropy Probe. And that produced some really terrific results. But it was already clear that WMAP was not the final step, and that we wanted to map the sky at higher precision.
WMAP had not yet launched, but we knew um, there would be more to do, and especially to fill in the smaller angular scales. And in particular, of all things, to go after N's of S, and because that was on the horizon. And to do the Zadolich effect and all those sorts of things.
We put together a group to make those next steps. Lyman had been working with, first starting as a postdoc with Mark Devlin when Mark was a postdoc at Princeton on ground-based experiments. And Mark had moved to Penn as a relatively new faculty member. And Suzanne Staggs, who I've known since she was a graduate student, and came back to Princeton after her postdoc and was, you know, pushing new experiments and technologies and making measurements of polarization. So the four of us came together to put together a proposal to build an experiment in Chile, which we called the Atacama Cosmology Telescope.
Well, I guess I started working on ACT as a graduate student when I first arrived at Princeton in 2002. And they had this idea to build a new telescope that wasn't quite funded yet, but said, okay, why don't we start looking at telescope designs? And was working with closely with Lyman Page and Suzanne Staggs and Joe Fowler at the time. And we just started exploring the parameter space of telescope designs for Gregorian and Cassegrain designs and a variety of different options to try to achieve a higher throughput telescope optics than people had achieved before for reflective cosmic microwave background observatories.
Actually, first person that was with me and Dave Wilkinson and Bruce Winstein was probably the first conversation. And we talked with him, and he said he was here on sabbatical. And he said, well, actually, I was thinking of putting in one from Chicago.
Of course, we were talking about doing something like ACT for a period of time before we actually put in a proposal, but then we did put in a proposal between Princeton and the University of Pennsylvania to build a 6-meter telescope up in 17,000 feet in Chile, based on work that some of our colleagues had already been doing up at that site.
We gathered the team and with Rutgers and Mark's group at Penn and the group here, which was and Arthur Kozlowski played a big role in that early on. And so we both put in physics frontier centers, and the one from Chicago, led by Bruce, won. So they got it and we didn't.
It was a long struggle. Like, our first proposals did not get funded. And, I remember going down and giving this presentation, and the four of us were on the train back from DC, and we were sure that presentation went well, and we were drinking beers on the Amtrak and relaxed and happy, only to find out we were just below the cut for funding.
Going back, even thinking of that first time, we all came back. I think after the presentation, it was Mark and David, Mark Devlin, David Spergel, and Suzanne and I, and we came back and, oh man, we sure we just nailed it, right? And no, and then in the failure report, it was, you guys are not a center. You are an experiment.
I think an important part of the story is also NSF kept at it, and the NSF staff helped make this happen. And we proposed again and would get funded. And, it's been, I think, from when we started on the proposal, 25 years from when we started to where we are now.
And we were funded by the National Science Foundation starting in 2004 to build this kind of crazy instrument, because it was a very large aluminum telescope made out of separate panels. The way that we did the actual camera, the first camera, was unusual, although now it's the norm, because we use separate optical paths for different frequency arrays. And then we were just running at this incredibly remote site, but the NSF was willing to kind of launch out on helping us to move forward with a kind of big visionary sort of step. And we got the telescope built, and we got first light, and we started to write papers, and then we went ahead and applied to upgrade the camera to include polarization sensitivity.
We proposed, right? The first proposal was just for 5 years, and then we were going to retire it. But then the science was great, and we kept figuring out how to do new things, and then polarization came along, and then we just, the CMB just was the gift that kept giving. Then we could do more things.
We put out a number of papers on scientific results from that. And then we decided we wanted to try to really upgrade the camera in sort of a final way to make this what is the most sensitive camera on Earth for these CMB experiments.
So it is so satisfying to basically take something over so many years and guide it for so long with so many people putting into getting the results, that it's just, when you see it happen, you see the final results, you're sort of in awe of what not just you were able to do, but what everybody's able to do when they put their minds to it.
And I guess regarding this evolution, I mean, just back to the telescope design side of it, one of the things that became clear from ACT is it was a great size telescope for pursuing a wide range of science goals. But we wanted even more optical throughput than it could provide once we'd filled out the focal plane quite well with the advanced ACT-Pol upgrade. And that's really driven the telescope designs for the Large Aperture Telescope for Simons Observatory and for the CCAT Observatory that just enable us to build larger instruments with many more detectors and get much greater sensitivity on the sky at both the millimeter wavelengths for cosmic microwave background measurements for Simons Observatory and the submillimeter wavelengths that we're pursuing with CCAT that are very complementary, but also going after a range of other science topics.
So I'm really excited about the Simons Observatory, which is just starting now. It's the set of telescopes at the same plateau in Chile. And it's kind of mind-blowing to me because I went there, I haven't been there for 15 years. And when I was there last, this beautiful plateau in Chile just had ACT on it and its neighboring telescopes, CLASS and Polar Bear. but it had this big gap next to it, and that space on the plateau is now covered in this new observatory, the Simons Observatory.
Jim was fascinated by the early universe, and he chose, when he was president, or chair of the board, Marilyn was president, um, to to start to fund the Simons Observatory. As exciting as the ACT results are that we're reporting, they themselves are a step along a path.
The age of the universe uh, is a controversial topic in cosmology. Some collaborations find one value of the age of the universe from the CMB, and then other from local measurements find another value for how old the universe is. And we hope that Simon's Observatory in the future will be able to settle this question on a single number and help us understand why these numbers don't match.
But I think more generally, there's a wealth of cosmological data sets coming in that are going to provide different angles to test the models that we looked at in these papers, and also potentially to find evidence or help develop new models in the future. So I think the main next step in cosmology is just to look at the data and see where it pushes us in some direction versus another.
I think what people should mostly do is to take a few minutes and go through these maps that we've made, and just just lose yourself by like imagining how big everything is. I don't know. It's really wonderful to see how far you can zoom in, and that every little dot you see is an entire other galaxy, or even a cluster of galaxies. Just wrapping your head around that is quite amazing, I think.
I think maybe what would interest normal people on the street the most is being able to just look at the maps. So I've made this interactive sky viewer that works much like Google Earth. You know, we have these huge maps, but which are too big to load into a normal browser window, for example. But by splitting it into tiles at different zoom levels, you can zoom in and pan around just like people do with Google Earth. And yeah, I think just being able to look around, see the CMB, and see the other foreground objects that appear in a multi-frequency way, so that different objects have different colors. I think that might be fun for people.
Quite often I see a paper in the morning and I'm like, oh, that's interesting. And I just start messing around with it, and 99% of the time, nothing comes out of it. But like that 1%, I try to replicate some method and I see something, or someone says like, oh, have you tried this? And I try and do it and it works and I get something out of it, and it might not be groundbreaking, but it was fun and I really enjoy doing it. And it's just something I could look at and something I get done. And yeah, that's I would say that just do it. Just try it, and who knows, it might work and it might be really fun doing it.
Being able to see the diversity and the types of people that are doing this work, and people coming from different backgrounds, they look different, they're doing schooling in all these different places, and like being able to like really showcase that, I think would be really impactful for the public, especially for like the younger kids trying to decide what they want to do with their lives. Because even if they don't want to do astro, them seeing people that aren't like the typical scientists doing something that's difficult might help them think like they can do something that's difficult, if even though they might not have initially thought that they could.
I mean, it has the right balance of all sort of roles and personalities, in terms of folks who have been in the field for a while and have a lot of experience with the theory and what it really takes to make these measurements, versus all the way down to junior level folks. But there's not so many of one or the other that it's becomes difficult to have conversations and informal conversations where kind of like actual learning and knowledge transfer and training of the next generation can happen.
I started working in the ACT collaboration during my PhD with Joe Dunkley, and just was completely blown away that I got to work with such an incredible group of people who are very passionate, very brilliant, and yet really kind, because the goal is to understand the cosmos.
I'd actually say one of the things that came out of this project not only was the tremendous science, but the tremendous scientists who joined as graduate students would follow along their career to become full professors. And now a lot of the most important work on the project is being done by students of these students, right? And, I like to think as a faculty member, we not only do create science, we create scientists.
I think it's very difficult to single out like a single result. And I always think the most impressive thing to me when I thought about this question was the amount of collective work that needed to happen for us to be able to publish the results. Because when you think about it, it started with like building the telescope, and then all these people working in the lab for years, like designing the little detectors, very sensitive detectors that we are using to capture the CMB photons. And then you start to take data, you have a lot of systematic, you need to do a lot of the calibration of the data. If any of this step goes wrong, basically, it could have been a showstopper. And everything went actually quite smoothly. And I think this is mostly because so many people actually worked extremely hard on this project and dedicate part of their life to make the publishing this result possible. So I think this is, to me, what's most impressive is kind of the collective effort, like on everyone pushing in the same direction, and that it went, smoothly, like after 2 decades of work.
We get a snapshot of, okay, we put out data release and here's what we think the universe is like. But it's always hard to realize, how much this builds on all the previous work that was done by literally hundreds and hundreds of people, not just in our collaboration, but in other collaborations, to get to the point where we can produce this.